To do the whole section. Oh, shocking. I have a doctor's appointment tomorrow, first and second hour, so I'm not gonna be here. So that, oh, that's a good start. I wanted to try to get through all of 2-3. That means officially we won't start 2-4 before the test. And then, so the test will be on 2-1 to 2-3. So I'll be back after second hour tomorrow, which doesn't help you really, most likely. On Monday, when we review, is basically when I will make sure to thoroughly go over 2-3 and any kind of questions you'd have. Let you know what's gonna be on the test, which is just 2-1 to 2-3. So you can pretty much already guess the test itself. 2-1 and 2-2 are basically the same section, just finding the derivative. I think what I'll do for tomorrow is, last time I printed out those little daily quizzes for you guys to kind of practice. I think for tomorrow, I'll give you the quizzes for 2-1, 2-2, and 2-3, just to see how it's going. And, 2-3, I wouldn't worry about it all yet, but you just try it. But then that way you can at least kind of get a handle on how you're prepared for the test. So, this section, if you flip through it, is a lot of pages. But in essence, it's actually only 2 topics. It's a lot of pages, yeah. There's a lot of tables. And so the lady that created the notes, what she likes to do frequently is introduce things ahead of time. And so this section, for whatever reason, has, I don't know, like 3 topics that are introduced ahead of time. And I don't know if I want to do that with you, given that we aren't gonna go past this section until October 23rd, like when we come back from ABA. So I figured I might as well just focus on the main topics, which is local linearization.
I have to run to the office. I need a pass for
Sounds good. Wait, you're already in there.
Yeah, but I don't know where I'm going.
Oh,
Maybe I remember.
that's important, gotcha. Local linearization, which actually we've kind of already done, and drawing derivatives, which we definitely have not done. Okay. First thing, local linearization gets its name because if you zoom in anywhere on a graph, if you zoom in far enough, it looks like a straight line. I know you guys have done that before. And if it looks like a straight line, then a straight line at that spot should give a pretty good estimate of the answer. So that's why they call it local linearization, is you're going to use a line to find the answer right there. I want to say we did it in the notes a couple days ago. I did it super briefly. Oh, actually, your class, I skipped it. And then we did it in the homework the day after. But I pretty much skipped it briefly because it wasn't that big a deal then. It was just kind of introduced early. Onyx, that's right, you're the new first person. Here, I know you probably want this. Okay. Who's gonna go?
5, 8,
We definitely don't have an 8. So let's, row 5 is this row.
3.
5, 3. Oliver. Do you remember what that straight line is called that we use?
Oh,
No? I'll take a drink
tangent
of,
line?
take a drink of tea. You got people you can confer with.
The tangent line?
I thought you said no. You're just randomly throwing out words now? You don't want to check with anybody? You try to tell them that you guys don't remember them? I've only said it like 500 times in the last week. Tangent line. 100% it was tangent line. You didn't sound super confident, so I wanted you to check. The tangent line is the straight line that mimics slope. So if you zoom in super far on any function, let's say I draw the tangent line at 0, it would look identical to the graph. If I could draw a straight line, it would look identical to the graph. Yes, that's true. That's a good point. So what we're gonna use is the equation of the tangent line to estimate, let's say you're asked to estimate that spot. We're gonna use, there's whole lot of things that we're gonna overlook, and like, you know, like some movies, there's like a billion plot loopholes. This is like one of those topics. There's a billion plot loopholes on this. Our goal is, if we are asked to estimate that spot on sine of x, we are going to use the tangent line at x equals 0 to estimate that spot on sine of x. Even though it feels like it should have been stupid easy from the beginning to just put it in sine of x. Like, there's a lot of reasons this shouldn't be done, and we're going to overlook that. Can you estimate the slope of this portion of the sine curve by inspection of this window? Actually, you know what? I don't want to do that part. There's a lot of boxes I don't want to fill in today. Let's do C, go right to it. Because I think you guys are smart enough to just know to do that. Equation of the tangent line for sine of x at 0. Oh, we haven't done the derivative of sine of x yet, have we?
No.
That's why this has estimation. Okay. What would you estimate the slope of that blue line? 1. Me too. Okay, we know the point is 0, 0. So we are going to use that information to write the equation of the tangent line. So y minus 0 equals 1 x minus 0. And this one, normally you don't simplify them. This one you want to simplify because there's a lot of zeros. So it's just y equals 1x. Roll.
All right, 3, 4.
Are we going to count people who are gone? Trevor, are we going to count people who are gone? Okay, fair. Elena, I think it's fitting. This is what we call karma. If I had to estimate...
Please excuse the interruption. At this time, students with the last names G through HA, please report to the black box for picture retakes. G through HA, black box for picture retakes. Thank you.
We're trying to estimate sine of 0.01. How would we estimate sine of 0.01 using our tangent line?
Would you just
Plug what in, but you are 100% correct.
Is it the equation we use?
No, I think what's partially harder about this one is our tangent line is extremely simple. Normally our tangent line would have a bunch of numbers and just a single x. What number would we put in place of that single x? Okay, perfect. So this one, when you put it in place of x, that's like the answer right away. So this would be our estimate of sine of 0.01 using the tangent line at that spot. So they call that local linearization. Now the reason I wanted to try to tell you what it was called is because I believe it's on the next page. There is a formula for local linearization, and a lot of people get kind of scared by it trying to memorize it. Maybe it's not this page. It's not this page. Good gosh. 4th page? All right, 4th page. That's the formula for local linearization. I don't wanna call on somebody specific. Does anybody recognize where the formula comes from? What do you, oh, derivative?
The, alternate formula, but
Oh, that's what you're pointing at too, huh? Honestly, I didn't even think that. It's not, but that's good thinking. I was assuming you're getting that from the A. Yeah, no, that's good thought, to be honest. Because you could use that for f prime of A. I didn't even think of it. Ignore that board. What does f prime of A stand for? Okay. What is A?
no.
A number? It's an x value. F of A is the y value. F of x is y. This is the tangent line equation, like directly. I'm not a fan of the fact that they write it as a different formula, but this is 100% how you will see it always written for local linearization. This is the same information as your tangent line. Remember I told you that the lady that makes these notes likes to write her tangent line, or point slope form, with the y value on this side. My guess is that's why she does, so that it matches up with the local linearization formula. But it is literally the point slope form of your tangent line. And all you would do, the reason I think they prefer this formula is because there's just a single x value that you would fill in with the number you're trying to estimate. Now, I would hope that you wouldn't use this formula until you have it filled out. And if you have this filled out, there should only be one x value free anyway. And so it should be the same. I just want to make, I don't care which formula you use either. I'm not trying to tell you not to use that one. I just want to make sure that you understand they're the same formula. And it kind of feels like you have to memorize something extra when in reality you definitely don't. Now, I think this is the page. Yes. Oh, sorry, go ahead.
So for the tangent line formula or normal line, and we can write it either way on just like the,
Yep.
with the y on the left.
Yeah,
and right
it doesn't
side.
matter which version of point slope you're at.
Okay.
Yep. Yeah, this is the one I wanted to do. This is literally, if you get to look at C, C would be the question that says use local linear approximation to estimate square root of 9.1. And this is kind of the steps we go through to get to there. You would be given square root of x. You would be given x equals 9. And then you would only estimate something very close to 9. So that's kind of how it works. It has to be set up that way. Elena, do you have somebody you want to choose?
What is it?
Wow, that was cruel. I think you said you did the,
It's been a couple weeks though. I'm not gonna remember.
not gonna lie, okay. So this is what we were focused on this week, was just the limit for a derivative, okay. Okay, pick somebody else, even though that you had good intentions. You had good intentions.
Sebastian.
I'm sorry. Yeah. You got people around you that can help you, even though I don't look like no one's trying to help you at all. I didn't ask one yet, but it was gonna be A. Do you wanna come up and do it? It is. Now, if you want to combine A and, no, A, we're just doing A. So, do you want Neil to come up with you? I feel like it's fair at this point, because he didn't even know what you were doing.
Sure.
Okay. Okay, the two of you, let's put the brains together. Let's figure out the slope at 9. And you can use whichever one of those formulas you want. Now, just remember, you're probably close enough for the microphone to hear you. Okay, just in case the whispering included some words that were not school appropriate. Good start, good start. Oh, nice, you even included limit. All right. Oh. Look at that big help. I like how you took your turn to write F prime of that. Oh, nice. You multiply by, we rationalize, so you multiply by the conjugate. Excellent. Look at you guys are acting like you didn't know what to do. This is one of the harder ones.
Can I write up here?
You're right, wherever you want. Now, this kind of seemingly is looking like some people's tests where the work is just wherever. In this case, I know it's because you don't have any room. What's kind of weird is you two are taking turns and the writing looks the same between every set. Yep, good. So now we want to know the slope at 9.
I'm coming back up.
Whoa, Neil, what happened to turns here?
Taking control.
Oh, okay. He wants the credit? Oh, look at that. That was very humble. Giving you the credit for the final answer. Don't blow it. Nice. All right. Okay, 1/6 is the slope. I'm hoping you guys can follow the arrangement they did up there. They did it perfectly. You multiply by the conjugate. The x's on the top cancel. That cancels the h from top and bottom. I would agree that there's not enough room up here, like on the whiteboard. You can probably write really small on your paper and fit it. But you should get to the end and get 1/2 root x. And then at that stage, we want the slope at 9, so we plug in 9. And that gives us 1/2 root 9, which is 1/6. Excellent job. Do you guys have somebody you would like to choose, or should I have Onyx roll the dice?
Can I roll?
Oh, wow. Oh, look at that.
6 and 3.
6 and 3. Oh, we don't have 3. Bless you.
It's 3 again. 6? 6 and 6.
We need a 1 or a 2. I mean, at this stage, you could just lie. Just say 1 or 2.
It's 2.
2. Onyx. Look at that. He stole the dice from you and called on you. Onyx, how do we find the equation of the linear approximation slash? How do we find the tangent line at 9? What 2 things do we need? What 2 things do we need for the tangent line?
Slope and points.
Okay, slope and a point. Do we have those 2 things?
We have slope.
We do have slope.
And we have, yeah.
It looks like Oliver is ready to call on somebody. Oh, unless you want to keep going.
Yeah, is it just, we just put in 9 for the square, so it'd be 6? Right?
Okay, you had the perfect plan, but I think you did the math in your head wrong. Square root of 9.
Square root of 9 is 3 times 2.
Oh, you were putting it in the slope formula.
Yeah.
No, I've already got the slope. 1/6. That's where you got the 6 from, got you. To find the point, you're gonna take the 9 that we had and plug it in the original function.
It's just point.
Yep, so this is gonna be the info we use for the tangent line, AKA the linear approximation. I'll write it like they do with the y on that side. So 1/6 x minus 9 plus 3. I should do a different color. Okay, now we want to take that info and estimate square root of 9.1. Oh, go ahead.
Can we still write it like y minus 3?
100%. Yep. You can write it whichever way you prefer, it still gives you an answer. Oliver, we need somebody to tell me what to write down for the actual linear approximation.
5 and 1.
Joe,
Okay,
blame Oliver.
what's up?
Blame Oliver.
I'm gonna get those dice then.
So how do I estimate square root of 9.1?
It's a great question, how do you?
Actually, I thought it was a good question. Oh, I asked it.
Well, we have that formula, would you plug in, square root of 9.1 into x1?
That's what I was trying to ask you is what number do I plug in there? So square root of 9.1 is the actual final thing that we're trying to estimate.
Okay,
This equation is going to estimate square root of x at x equals 9. So if we're trying to estimate square root of 9.1, you actually only plug in 9.1.
yeah.
That's generally the hardest part of these problems is figuring out what to actually plug in. So I would do y equals 1/6 9.1 minus 9 plus 3, and we're gonna do this in our heads. Sounds ridiculous. So 9.1 minus 9 is 1/10. You almost lost your teacher to a heart attack up here. 0.1 is 1/10. That was probably the loudest metal bottle I've ever heard fall. So we've got 1/60th plus 3, and I know you guys are smart enough to just write the answer as
3/60.
you meant correctly, but did not pretend you didn't say that. What? Whoa, you guys are putting so much work into this. There we go. 3 and 1/60th. Why would you change that to 181/60th? I mean, it's not wrong, but like I was hoping you guys would do the easy version, which is just as accurate and correct.
It's not times 3. Yeah.
Oh, you were
It's
multiplying.
not times 3.
Are we assuming the y value barely changes?
Yes. And honestly, if you take your calculators and do square root of 9.1, hit enter, and then do 3 and 1/60th, hit enter, you should get very close answers. I'm sure that's probably E on the bottom, I don't know. I didn't read it yet. What's square root of 9.1?
3.016.
3.216. And then this one is, I don't know, 3.0 something.
Oh, 1/6.
Okay, well, they're clearly not the same out here, but,
Well,
yeah, but they are very close. So that's why the idea of, if you pick a number close enough to 9, the tangent line and the normal function will have very similar answers. Okay, this was one idea. Perfect. Our second topic for today is drawing derivatives. I don't think this is the page I wanted to go on? Oh, it was this page. That's, the notes for this section I didn't really like because it felt all over the place to me. and there is only 2 topics. Who's singing? That was Joe.
Yes, it was Oliver.
I can see it. Got a nice voice. We are going to be drawing the derivative of the function that's in black. On your paper, I don't know how difficult it is to tell between them. What's written up there is 2 of the tangent lines at random spots. You got the roller. Oh, what do we got?
2 and 6.
What does a derivative tell us again? Perfect. So if we are going to be drawing a derivative, this is going to be a drawing of the slopes of f. So f prime is the slopes of f. And you're going to want to keep that in mind as you are drawing the derivative. So the height of our derivative represents the slope of the original. So that's why these 2, the red and the blue line, are here. We're going to estimate their slopes. I gotta think that looks like about 1. Okay, where am I going to draw a slope of 1 on the derivative? And I don't know if I want to call on somebody for this one. Does anybody feel like they know? Which x value of the derivative is going to have a slope of 1? What's the x value of this one? 1/2-ish, yeah, I don't know, I can't tell. Does it? Okay, I'm gonna pretend that I knew that. So exactly 1/2, looks like it has a slope. It even says the answers to the slopes. I don't like that. Pretend we don't see that. I guess we'll write that on there then, okay? It's cheating. So if the x value of this point is 1/2, then on my derivative, I'm going to go to the x value of 1/2, but the height of the point will be 1. Because my slope was 1. This graph is telling me the slopes of that one. Okay, so this one is an x value of 4, and apparently we are told it is exactly 1/3, although it says about 1/3, but whatever. Over here, at an x value of 4, I will make the height 1/3. And you estimate. Okay.
Wait, could this just be considered like a graph, basically? Or you're like, you're just
Not basically.
like,
I think what you're trying to ask me is plotting points type graph?
yeah.
Yes,
It's just, yeah.
that's exactly what we're gonna do. We're gonna plot some random points and predict a graph from that. But yes, your first question, it definitely is a graph. All right, so at this stage, I'm just gonna kind of estimate a handful of more slopes. What about really close to 0? What is my slope? It's really steep. So yeah, let's just call it 10. I don't know. Oh, I'm not gonna call it 10 because that only goes up to 4. Let's just say it's 4. Really close to 0, it's at 4. And then judging by that graph, I kind of want some answers in between here. So if I look at 2, it's flatter than 1, but steeper than 1/3. I don't actually have to know the number. I just know it's going to be between 1 and 1/3. So at x equals 2, put it in between them. What if I pick I mean, I'm gonna say 7, but let's pretend as this graph goes out farther, what's the slope gonna become? It's kind of slowly turning into 0. Slowly. It's not gonna get there forever. But the slope is slowly flattening out. So at 7, it's tiny. Now, if I had a negative slope, where would I put that? Below the x-axis. This one specifically is drawn there because these are all positive slopes. So then I would draw a nice smooth derivative from my points. I'm not going to actual connect the dots. I can tell that this is becoming a curve. As best as I can draw, you're probably better than me. That looks like it is roughly the derivative of square root of x. Now, I don't want to teach you how to cheat on your calculator yet, but I could have your calculator draw it for you. What time do we go till? 6? If you want to draw this on your calculator, the derivative is going to be 1/2 x to the negative 1/2. Make sure your power has the complete negative 0.5. But if you draw it, it should look like that. If not, we screwed up badly. I mean, you don't know the derivative yet, but that's fine. That's what it looked like? All right, good. I still can keep my job. Granted, I guarantee I'll screw up at some point this year. Okay. I think this one had it already drawn, didn't it? Yes. Okay, here's the most important mistake that you're gonna make. You're gonna look at this one and say, what kind of graph is this? Or you'll look at this one and say, what kind of graph is this? Parabola. So what do you know about parabolas? What do they look like when they're x squared? You're probably going to think this is cubed. Don't go by that. You don't know anything about them if you're not told the equation. The only thing you know is what's drawn. So up above, we didn't have one of these spots. What is probably the easiest slope to locate on a graph? To identify, exactly. 0. Well, yeah, 0. I mean, they're both correct. Looking at this first graph, I have 2 spots that exactly have a slope of 0. Now I'm going to take these x values, and what is going to be the height of my graph on the derivative? 0. And conveniently, because this is already drawn, but if you were drawing it yourself, this is a nice, easy spot to draw. So a slope of 0 there and there. And we're going roughly estimates. I'm not looking for exact anything when you draw it. So those are always the easy spots to identify and locate. From there, then you try to estimate. That looks like 2, 3, I don't know. Steeper than 1. So x equals -4. Oh, apparently it's 6. Oh, actually, it's not going to be 6, but whatever. Even if you put yours at a height of 2, that would be correct. What I'm mainly looking for when you draw your derivative is rough estimates. I will not be looking for exactly correct, because you won't know equations. As I get closer to the flat line of 0, I've got a slope of 1 somewhere in there. So somewhere at roughly -2, I would draw it height of 1-ish. Looks like this one's up at 2. Now, in between these flat spots, what are all the slopes? they're all negative, because it's pointing downwards. So that means in between these zeros, it will be below the x-axis. So positive slopes above, negative slopes below, positive slopes above. So without even having a drawing, I know where my drawing should be. So above x-axis, 0. Below x-axis, 0. Above. Okay? And I kind of got that drawn so far. I'm just going to go right in the middle because this is my steepest negative number. And a lot of graphs are symmetric, so you kind of already know that. So this looks like at roughly negative, at roughly 1 or 2, somewhere in there. A slope of -2. And in between 1 and 2-ish, a slope of -2. And then if I wanted to estimate some more spots, the more you pick, probably the easier it is to draw. That's about a slope of 1 by 5. And this was steep, so it would be up there. And then if I didn't have this black line there, I would be able to predict a parabola drawing.
Can you really quickly explain how you understand the slope from seeing this?
I mean, like, how did I guess 2, 3, 4?
Yeah.
1. 0. Half. You roughly guess it. Steeper than 1 is where most people have the trouble. I'm totally guessing. I know straight up and down is infinite. I don't know, 2, 3, 4. I'm not going to be looking for exact anything. I am mainly going to check if you know the slope is greater than 1 or less than 1. That's the main thing that the AP will look for when you draw it as well. So that's kind of why I was saying when I drew it, I said it looked like 2, and it was actually at 6. It's rough.
Excuse the interruption.
But I judge everything by
Students with
1.
last names H-E through I, please report to the black box for picture retake. H-E through I, picture retake in the black box. Thank you.
We got 5 minutes left. See if you can draw this one. Now, I will do my best during R&R today to look to see which homework questions you should do. Because I would bet there's a bunch in the homework you don't need to do. So I'll check tonight during R&R and cut some out. And I'll write that on in Schoology. So don't sweat it if you're trying the homework and there's a bunch, because I wanted to skip the ones that we're not gonna focus on. Like the ones that aren't actually part of this section. But see if you can draw this derivative. Start with the easiest spots and go from there. Hello? Hi. Sure, could you come down in a couple minutes? Okay. Yep, okay. Did you skip an hour?
No,
That is a
it's
guilty,
because I was gone yesterday.
that was a guilty look.
No.
No, yeah, I definitely didn't do that. Olivia, did that sort of help about the
Yeah.
guessing at least? Okay. I don't know, I just kind of go in my practice mostly. I judge everything by 1, because that's the only one I actually know. Oh, these are bad spots. Whoa, guess those are the points I would have used to try to predict. I picked the zeros first because they're the easiest. I picked the spot in between the zeros. And then I picked a couple spots on the line that was bendy. And that kind of predicts my graph. So this is roughly my derivative. Okay, that's all I got for the whole section.